Assalamualaikum everyone. Today we are presenting our project titled Diabetes Disease Classification Using Kenya's Neighbors, a machine learning approach designed to predict diabetes. This project was created by Boktiar Rahman Jowaraj, Mahir Ahmed Hanaf, and Khalid Hassan. Before we dive into the technical details, it's important to understand why this project holds immense value in the field of healthcare. Diabetes is a chronic disease affecting over 422 million people worldwide, with the numbers continuing to rise. Without timely diagnosis and intervention, diabetes can lead to severe health complications like heart disease, kidney failure, and nerve damage. The goal of our project is to explore how machine learning, specifically Kenya's neighbors algorithm, can be used to classify and predict whether a patient has diabetes. By using clinical data from patients, we aim to build a predictive model that can support healthcare professionals in identifying diabetes early and leading to their better health outcomes. Moving to slide 2, we delved into the background and objectives of the project. As mentioned earlier, diabetes is a widespread and serious disease that requires early diagnosis for effective treatment. Unfortunately, many cases remain undiagnosed until the disease has progressed, and making early detection crucial. Our project utilizes machine learning to address this challenge. The aim is to predict diabetes using a classification algorithm based on a patient data. Specifically, we employed the Kenya's neighbors or KNN algorithm. The reason we choose KNN is because it's a simple and powerful classification method that works by comparing patient data to the data of others. The algorithm looks for patterns and similarities in clinical features like glucose levels, insulin levels, and age to classify whether a person is diabetic or non-diabetic. KNN is a non-parametric, meaning it doesn't make assumptions about the underlying data distribution, making it highly suitable for healthcare, where patient data can be quite varied. By applying this model, we are able to quickly and effectively predict diabetes risks and support the healthcare professionals in their decision making. Moving to slide 3, dataset overview. We give an overview of the dataset used in our project. We utilize healthcare diabetes dataset from Kaggle, which contains 2,768 records of patient data. The dataset includes 9 important clinical variables such as glucose levels, insulin, age, and body mass index. These variables are crucial indicators of diabetes. The target variable in our dataset is labeled as outcome, where 0 indicates non-diabetic and 1 indicates diabetic. The dataset is rich in the kinds of information that doctors typically analyze when diagnosing diabetes. For instance, glucose levels are one of the most significant factors, as uncontrolled glucose is a hallmark of diabetes. By feeding these features into our machine learning model, we can analyze how these variables interact with each other and help predict whether a patient is diabetic or not. The value here is that the machine learning model can process large amounts of data quickly and reduce predictions that assist in the early detection of diabetes. I forgot to say my name. It was Khalid Hassan. Now I'd like to give the floor to Bhakti Rahman. Thank you.
Thank you so much, Khalid, for introducing us to the project. Hi, I'm Bhakti Rahman Tumorans, and I will be covering the pre-processing part and the code implementation part of this project. Now, let's dive into the pre-processing steps that were critical for ensuring the data quality before running any machine learning models. Pre-processing is essential because raw data often contains missing values, outliers, and inconsistencies that can negatively impact models' performance. I'll walk you through the main steps of how we prepare the data. Our first step in pre-processing was conducting an exploratory data analysis, or EDA. We begin by examining the first and the last few rows of the dataset to get a feel for the structure and values. The dataset contains 2,768 records and 10 columns, including features like pregnancies, glucose, insulin levels, and outcome, which indicates whether or not a patient has diabetes. We also looked at the basic statistics using the describe method, which gave us a sense of distribution of each feature, including mean, minimum, and maximum values. These steps allowed us to identify potential issues such as missing or zero values in the dataset, especially in columns like insulin and skin thickness. Next, we addressed missing values. Initially, there was no explicit missing values marked as none. So we noticed that certain features had zeros in places where they shouldn't. For example, features like glucose and BMI had zero values, which is unrealistic in medical dataset. To handle these, we used a technique called imputation. We applied the simple imputer with the mean strategy. This replaces zeros with the mean values of the respective column. This is a common method in healthcare dataset to fill in plausible values, especially for continuous features. After applying this, we had a more reliable dataset with no missing or zero values in the critical columns. Once we addressed missing values, the next step was feature scaling. This is important because our dataset contains features like different ranges. For instance, glucose ranges from 0 to nearly 200, while BMI ranges from 0 to 67. To bring all the features to the same scale, we used min-max scaler. This method scales the values to a range between 0 and 1, which ensures that each feature contributes equally to the model's performance. For example, glucose values that were between 0 to 200. For example, glucose values that were between 0 and 200 are now in the range of 0 to 1, making it easier for the model to process. Next, we dealt with outliers. Outliers are extreme values that can distort our model's understanding of the data. We used the interquartile range or the IQR method to detect outliers in features such as insulin, skin thickness, and age. This method calculates the range in which the central 50% of the data lies, and any value outside this range is considered an outlier. After identifying these outliers, we removed them from the dataset, which reduced the dataset size. This step ensured that our model wouldn't be skewed by these extreme values, which could have negatively impacted its performance. Finally, before training our model, we split the data into training and test set. This is a crucial step for evaluating how well our model generalizes to new data. We used an 75 to 25 split, meaning 75 of the data was used for training and 25% was used for testing. By doing this, we ensured that the model isn't just memorizing the training data, but is also able to perform well on unseen data. This concludes the pre-processing phase. We ensured that our data is clean, scaled, and ready to be used in our machine learning model. Once our data was pre-processed, we implemented the KNN algorithm for classification. KNN works by finding the closest data points to a given sample based on a distance metric, typically Euclidean distance. For our model, we set k equals to 2, as this provided optimal performance during testing. We trained KNN using the pre-processed training data, and during the evaluation, the test set, the model achieved a high accuracy of 95%. The confusion matrix showed a strong performance, correctly identifying both diabetic and non-diabetic cases. Thank you.
Assalamu alaikum everyone. My name is Mahirana Ahmed and I am the last presenter of this group. Now let's look at the performance of our Canon both before and after handling outliers. Before handling outliers, the training accuracy is 98.98% and the testing accuracy is 94.51%. While the model performed well on training data, the testing accuracy was slightly lower and indicating potential overfitting. After handling outliers, the training accuracy is 99.21% and testing accuracy is 95.75%. By removing outliers, especially in features like insulin and BMI, the model's ability to generalize improved, resulting in better testing performance. On to the next slide. To further evaluate the model, we used confusion metrics and three key matrices such as precision, which indicates how many of the cases predicted as diabetic were correct. High precision suggests the model is good at minimizing false positives. Recall measures how well the module identifies actual diabetic cases. This is important in medical diagnostics to ensure all diabetic patients are correctly diagnosed. And lastly, the F1 score balances the precision and recall, giving us a better measurement of overall performance. A strong F1 scores indicates that the model efficiently identifies diabetic patients with fewer misclassification. Together, these metrics show that the model performs well in identify both diabetic and non-diabetic individuals. And now, in the conclusion, our KNN model achieved an accuracy of 95.75% with better performance after handling outliers. This highlights the importance of data pre-processing in improving model performance. Moving forward, we plan to apply the model to larger dataset to further test its robustness and scalability. Compare KNN with other algorithms such as logistic regression, decision tree, random forests to see if they outperform KNN. Optimize hyperparameters like the value of K and experiment with different distance matrices for potential improvement. In summary, KNN performed well, but there is room for further refinement and testing on larger datasets. Okay, thank you very much.